We are now going to talk about the ideal gas law. In the prior videos, we've talked about Boyle's, Charles, Gay-Lussac, and even the combined. All of those gas laws had a before and an after scenario. The ideal gas law is the one that does not have a before and an after, which is your one clue to know when to use the ideal gas law. Instead of a before and an after, the ideal gas law compares the current conditions to standard conditions, or R. The equation for the ideal gas law is PV equals nRT, or Pivnert. You should be given a variety of these variables, whether it's P, V, N, R, or T. You might be given some, you might be given none. You might have to use the standard conditions. If you need to use the standard conditions are P for pressure. If it's ATM, it'll be 1. If it's kilopascals, it'll be 101.3. If it's torrs, it'll be 760. The volume is 22.4 liters per mole at a standard condition. A standard condition for amount would be 1 mole, and the standard temperature is 273. Now, there's one variable in here that we haven't talked about yet, and that is that R. R is simply found by plugging standard P, V, T, and N into one side of the combined gas law, and you'll get the appropriate R value based on the pressure. So, if your pressure is in kPa, you will use 8.314. If it is ATM, you'll use 0.0821. And if it's in torr or millimeters of mercury, you're going to use 62.36. You now want to pause your video, gather your materials, a calculator, something to write with, and a periodic table to do some practice problems. We're going to do some practice for the ideal gas laws. Just a reminder, our formula is PV equals nRT, or Pivnert. P is pressure, V is volume, which has to be in liters, N is amount, and it has to be in moles, and R is rate. You have those rates. They were given to you in a previous slide. Your rate needs to match the pressure, so whatever unit pressure is in, you want to choose the R that matches it, and then T is temperature, and just a reminder, it has to be in Kelvin. So one thing remember to look forward to in the Pivnerts or ideal gas laws is there is no before and after scenario, kind of like combined was. Pivnert is just pretty much straightforward. So all of these are going to be Pivnerts. So we know it's Pivnert or ideal, so we're going to write our variables P, V, N, R, and T, and we can fill them in. So it says a 0.68 mole, so that's amount, of CO2 gas has a pressure of 2.5 atm and a temperature of 30 degrees Celsius. We don't want Celsius, we want Kelvin, so we need to add 273, so we get 303. What is the volume of the gas? So that's our X. Now some of you are going to say, I don't have an R. The R was given to you on a previous slide, so if you need that, go back to it. Our pressure is ATM, so you have to use the R that's associated with it. 0.0821 is the R that we're going to use for it. We know the equation is PV equals nRT, so 2.5 is P, V is our X, N is 0.68, R is 0.0821, and T is 303. So we can solve for X, 2.5X, and then we're going to multiply 0.68 times 0.0821 times 303 gives you 16.9. We're going to divide each side by 2.5 to get X by itself, and then X equals 6.76. We're looking for volume, so you know your unit is going to be liters. Take a few minutes to solve, and if you have questions, make sure you ask your teacher. Let's try another one. Number 2 is what is the temperature? Once again, we're doing ideal. So P, V, N, R, and T are our variables. Temperature is going to be our X. We have 0.005 of moles. We have 0.18 liters. And our pressure is 1,000 torr. Okay? So, since our pressure is in torr, we're going to use the R that matches it, which is 62.36. We know the equation is PV nRT, so 1,000 times 0.18 is equal to 0.005. Our R is 62.36, and our T is our X. So 1,000 times 0.18 is 180. 0.005 times 62.36 is 0.3118x. We're going to get x by itself by dividing 0.3118. And then x will be 577.29 is equal to x. Now, since it's temperature, we know temperature is always in Kelvin. And that will be your final answer. Take a few minutes to solve. Check your answer with mine, and we'll do 2 more problems together. Number 3. We know it's still ideal, so P, V, N, R, and T. We have 25 grams of water, okay? Except we don't want grams, we need moles. So we have to convert grams to moles. If you have grams at the top, you need grams at the bottom. If you look at the periodic table and get the molar mass of water, it is 18, and that's equal to 1 mole. So 25 divided by 18 is 1.4 moles. It's heated to 350 degrees Kelvin, and it's confined to a volume of 30.5 liters. What is the pressure is our X inside the container, okay? It does not say, so we're gonna go ahead and just use ATM, and our ATM is 0.0821, and then we can plug it in to solve. So we have P, our volume is 30.5, our N is 1.4, our R is 0.0821, and our T is 350. So 30.5 P, or X, 1.4 times 0.0821 times 350 is 40.229. Divide each side by 30.5. And our X is 1.32. And since our pressure, or our R was in ATMs, we're going to use ATMs for pressure as well. So 1.32 ATM. Okay, take a minute, check yours to solve mine, and we're going to do 1 more problem together. All right, we know it's still ideal, so I'm still going to list my variables. You should always start by listing your variables, P, V, and R, T. We're looking for moles. Our moles is going to be amount, which is X, are required to fill 2 liters at a flask of 173 K and a pressure of 950 torr. Okay, so we're still missing R, but R is a given variable. If you need those lists of variables, go back and check a previous slide. So for torr, we know we're going to use 62.36 as the one that matches the P. Once again, our equation is PV and RT, so 950 times 2 is equal to X times 62.36 times 173. So 950 times 2 is 1900 to 62.36 times 173 is a really large number, 10,788.28. We're gonna, and that's our X, so we'll divide each side by the large number to get X by itself. So 1900 divided by 10,078, and you get 0.176. And we're looking for N, so N is moles. Take a few minutes to see if yours matches mine. If you still need help with the ideal gas law, make sure you check in with your teacher.